Okay, now for the second problem, final practice problem. We have a piping assembly here, and it has an outside diameter and a wall thickness. So I labeled the outside diameter, I calculated the inside diameter here. The assembly has 3 different loads. It has a PX of 320 pounds, says here. It has a PY of 410 pounds, and it has a PZ of 180 pounds. Then I labeled the dimensions. We're supposed to find the normal and shear stresses on the outer surface of the pipe there's 4 points available, but I'm just going to do A and C. And then I posted the solution for all 4. And then we need to, of course, show these stresses on an appropriate sketch with axes shown. All right, so this problem's pretty fun. So what we're doing here is when we start by looking at A, we're going to have a bending stress from PZ. So that's going to be, we're going to have the PZ here is going to be a moment around X. So we'll have a positive moment around X from PZ. And this will also create a positive moment around X at CD. PY is also going to create a positive moment around X. So we will have 2. That means that they're both positive. We'll add them together. So that's from PY. And then we have PX is going to, twist this thing around the y-axis, right? So now we're going to have positive moment around the y-axis. PX is also going to twist this thing around the z-axis. So this is from PX, and then we also have this moment around Z that's going to be negative. So, and that will be from PX. So we have a lot going on here. Okay, we can handle this. So we can start by calculating all the section properties we're going to need again. So we have I equals pi over 64 times outer diameter to the 4th minus inner diameter to the 4th. I'm not going to write all those out, but we get 28.8 inches to the 4th. Our polar moment of inertia is pi over 32. That's big D, outer diameter to the 4th minus inner diameter to the 4th. It's twice the I, so we get 57.6 inches to the 4th. Q, since we have a circular shape, we will have 1 over 12 times outer diameter not to the 4th cubed, outer diameter cubed minus inner diameter cubed. And that's going to be 5.73 inches. And then in this one, PY is going to cause an axial load here. So we'll have an axial load there. PZ, is going to cause an axial load here. So we have axial loads this time, which I have that equation here. So this time we have bending we have bending shear, we have torque, and we have axial. So everything's going on here. So we need the area. Area equals pi over 4 times d outer, not to the fourth. Get too comfortable with that. D squared minus inside d squared. And that equals 5.63 inches squared. This is inches cubed here. Okay, so those are our section properties. Now we're going to cut at A and B. We're going to draw equivalent force systems. So we're going to move these forces down to A and B. Because we move them, we have to then acknowledge the moments that happen due to moving the forces. So we're going to draw two free body diagrams at AB, one of forces and one of moments. So here are our free body diagrams at A and B. So the first one is forces. Draw our circle. We have A here, we have B here. The reason why I know that is because I'm going to draw my axes where I have Z and X. That's not very good, X. So that's looking, if we're looking at A, we have, or if we're looking at this cut here, we have Z coming out this way, and then we have X coming out this way. That's what we're drawing. Okay, so now we draw those forces. We're going to have a P, this is PZ, and it equals 180 pounds. We have a PX. That's, can't draw a straight PX. This is PX, and that equals 320 pounds. And then we have a PY acting longitudinally along the axis of the pipe, and that is 410 pounds. All right, so now let's draw the moments that we're gonna find here. So we have A here, B here. All right, so let's start with X. So we have a moment from PZ around X. So that's going to be a moment, we're going to take PZ times this distance, 4.5 feet. Okay, but we have to add that to the moment from PY, which is going to be this 410 times 3 feet. Okay, so we're going to have, for MX, we will have positive moment that equals MX equals 180 times 4.5 feet plus 410 times 3 feet. So we get a total MX of 2,040 pound feet. So that's our moment around X. Okay, so how about our moment around Y? That is going to be, in this case, cos from px, and it's going to spin this around in the longitudinal direction, so that's going to be our torque. So we have my equals torque equals 320 pounds times 3 feet, so that's, we have this 320 times this 3 to spin this guy around, and we get 960 pound-feet. Then, lastly, in the z direction, we're going to have px spinning this, bending it. It's going to be bending it around z, so it's going to be this 320 times this 4.5 distance. So we have, and that acts in the negative z direction. So we have mz equals 320 feet times 4.5, or that's 320 pounds. Times 4.5 feet, and that equals 1,440 pound-feet. All right, so in the solution I gave you, I wrote all those out, but we're just gonna jump into point A. Point A. So, first thing we're gonna do, I think it's the easiest, we're gonna look at this axial stress from PY. All right. So we have axial stress from PY. So that equation, it's going to act in the longitudinal axis. So it's going to act along Y. So this will be a sigma Y. A normal stress in the y direction, and it's just the py force over the area, and we get 410 pounds all over. Our area that we calculated was 5.63 inches squared, and we get 72.9 psi. Then we look, that's going to be pushing down, so it's going to be putting this in compression. So we're in compression. First stress. All right, next stress. Let's look at the shear stress that's going to be caused from px. So px of 320, we just move it down to the top here of A, and we will look at the shear stress from px. So this would be a bending stress, so tau equals the shear force times Q all over I times T. T is the big diameter minus the little diameter. The px force is 320 pounds. Q is 5.73 inches cubed. All over I was 28.8 inches to the fourth. And T is big D, so this captures the thickness of the wall on both sides. Big D is 6.675 minus 6.115. Those are inches. So this bending shear stress is 113.6 psi. Now let's draw a stress block of that. The stress block means nothing without labeling the axis. The axis, when we're looking, I'm going to look straight on at A. So that axis that we're going to have is the XY axis. And this arrow that we drew is acting in the positive X direction on the positive Y face. So we go back here. Have this. We draw in our axis. We have X. We have Y. We said it was acting in the positive X direction on the positive Y face. Opposite on the bottom. Match the heads and tails. All right. Now we have the normal stress, the bending normal stress. From the moment about X. And that was, remember, the moment from PY and the moment from PZ. So this was a combination. So MX is this 40 pound-feet. All right, so bending normal stress equation, sigma, this is going to be in the Y direction. It acts in the longitudinal direction of the pipe. That equals my over I. This is mx, which was 40 pound-feet. We need to get rid of the feet, so multiply it by 12 inches per foot. The y is the radius of the big diameter, so 6.675 over 2 inches, all over I was 28.8 inches to the fourth, and we get 2,835.7 psi. Now we need to look and see if that's in compression or tension. So both of these are positive moments. They're both going to bend this pipe like that. Never mind, yeah. They're going to bend the pipe. So, they're going to have compression. So they're going to, they're going to bend it like this. Sorry, keep getting confused. Putting that in compression. Bend it, yes. All right, so we have compression. All right. Lastly, we have the shear stress from My, which is the torque. And that's the torque. So that is what is spinning this thing around. So that's going to spin it in the same direction that the shear acted. So we have the torque equation is shear stress equals T, which in this case is just my, times C, just the radius of the big diameter, all over J. So 960 pound-feet times 12 inches per foot times 6.675 over 2 inches, and that is all over 57.6 inches to the fourth, and we get 667.2 psi. We said it was going to spin it. The shear stress was going to be the same as the direction of the bending stress. All right, so here we have PZ does not cause a shear stress at A. I demonstrated at the last video and in class a number of times. And the moment about Z does not cause a bending stress because A is at the neutral axis for that moment at A. But if we were looking at B, those two would be in play. All right, so then we summarize this in a stress block. This is A. It's very important. We label our axes here. We have two shear stresses that we're going to add together. They're both going the same way. We have the torque shear stress, and we have the bending shear stress. So and then we have two compressive forces in the Y direction. We have the axial compressive force and we have the bending compressive force. All right, so bending was 2836. The axial was 72.9. The bending shear was 113.6. These are all PSI. And the bending torque was 667.2. So to draw the final shear diagram, since these are both going the same way, copy this over here. We'll add those two shear values together to get 781 PSI. We're going to add the two compressive stresses together to get 2,909 PSI. So that is point A. All right, let's look at point C. We'll look at point C. We need to draw free body diagrams at C and D. So now what we're doing is cutting it here, moving all these forces to here, which means that we have to add the moments there. So we're going to have a free body diagram of forces and a free body diagram of moments. Here we have forces. All right. We draw our circle. We draw our axis. It's going to be X and Y. And we draw another circle. Really drawing these big. Okay. So for forces, in the X direction, we have PX, it's 320. We have PY, it's negative 410. And we have PZ, the axial force now is 180 pounds. PZ, PY, and PX. All right, these moments now are going to be, so we still have these moments, 2 moments coming from PZ, but what's going to change is what we, 2 moments around X from PZ and PY. So from PZ, we're going to have now Y1, that didn't get copied, is 2 feet. So now our distance, we have to go all the way. So our force stays the same, our direction of the moment stays the same, but when we calculate the moments, our distances might change. So now we have 6.5 feet, but they're both going to change. And then when we're looking at the moment around Z, that's also going to be a distance of 6.5 feet. And when we're looking at the moment around Y, that'll also be a distance of 6.5 feet from these Z dimensions. Okay, so calculating all of our moments. So, in the X direction, we have 2 positive moments. So we have 180 times 6.5 feet plus 410 times 6.5 feet. And that equals 3835 pound-feet, and that is our moment around X. Our moment around Y is positive, and we have, this is 320 pounds times 6.5 feet. And we get 2,080 pound-feet. And then the Z moment is negative And this is 320 pounds times 6.5 feet. And this equals 2,080 pound-feet, and that's mz, which is going to be our torque. And that was m1 right there. All right, so using all of that information to look at point C, we're going to have an axial stress again because we have this force in the longitudinal direction. So this time the axial force, the axial stress is going to come from PZ. All right, so we have, that's going to act in the sigma z direction. So the stress will act in the z direction. It just equals the force PZ over that area. So we get 180 pounds over 5.63 inches squared. And we get 32 PSI. We look at how that's acting. PZ is pointed out, so it's going to be in tension. So tension along the z-axis. All right, now we're going to look at the shear stress from PX. So we have PX here. If we draw PX on here, it's going to be acting in the positive x direction on the positive z face. So shear stress from PX. So we get tau equals V, that will be PX, times Q. Calculated that, it's the same throughout the problem. I is the same throughout the problem, and T is the same throughout the problem. The big diameter minus the little diameter. So the thickness times 2. So that equals PX is 320 pounds. Q is 5.73 inches cubed. All over I is 28.8 inches to the fourth. And D, the T equals big D, 6.675 minus little d, 6.115. These are all inches. And we get 113.6 PSI. Now we need to know what orientation that is in. We draw our stress block. Doesn't mean anything without the coordinate system, which in this case is X and Z. So we're looking down on the top of this pipe. So we have Z coming out that way and X coming that way. All right, and we have on the positive Z face, the shear stress acts in the positive X direction. Wait. So PX comes down in the positive Oh yeah, positive X on positive Z face. This is where it gets confusing and how you draw it. So our positive Z face is over here, and our positive X direction is going down, which I'm not used to, but it's all good. It's just making sure. That's why we have to draw our axis, and that's why I think it's very helpful to draw these little stress blocks along the way. All right, moving on. The normal stress from the moment about X. From MX. Okay. So this is going to make the beam bending stresses act. They always act longitudinally. In this case, it's Z. So we have sigma Z equals the moment about X times Y, which is the radius of the big diameter, all over the moment of inertia. This equals 3,835 pound-feet times 12 inches per foot times the radius of the big diameter, 6.675 over 2 inches, all over 28.8 inches to the fourth, and we get 5,331 psi. Now we go look to see if this is in compression or tension. So this is from the moment about X. So we're going to be bending it this way. So it's going to be in tension. C is in tension. Underline that, that's important. And it's in tension. Alright, lastly, we calculate the torque, which is the shear stress from MZ. MZ is the torque. So we have shear stress equals the torque, or MZ, times C is the radius, all over J. So we have 2,080 pound-feet times 12 inches per foot times 6.675 over 2 inches, all over J, 57.6 inches to the fourth, and we get a shear stress here, 1,446 psi. Now, we need another stress block. So, we need a stress block. It's going to have the same axes as the last one, Z and X. I'm going to go look at what's happening up at our picture, all this work ago. This is twisting it this way, meaning it's going to go in the same direction as our last stress block. So that's nice. Then we just have to draw it the exact same way. And we'll add those together. Alright, so our final stress block will be adding this tension force to this tension force. We'll have two tension forces that are added together. And then this shear stress plus this shear stress are both going the same way. So we'll draw our block. We will definitely draw our axis where we have z positive this way, x positive this way. Our shear stress goes like this, and it is adding the two shear stresses we calculated together. So this is 1446 plus 113.6, and we get 1559 psi. And then we have tension in the z direction, the longitudinal direction, block C, and that equals this 5,331 plus our 32, so we get 5,363 psi. So that's our stress block. And then I'll let you all do D and B on your own, and I've posted those solutions. So I think if you guys have a pretty good handle on these problems, you will do wonderfully on Monday.